Hey everybody, this is Jess Friesma, giving mini lecture number 9 for Computer Science 163 at the University of Wisconsin-Eau Claire. We'll be talking today about linear search, a linear search algorithm, the linear search algorithm, and it's talked about in a little more detail in section 6.2.6 in your textbook, and then also in more detail in 12.6.1. I encourage you to check them both out, and notice that you might notice that chapter 12 is actually not in your book. That's because it's online only, so you have to access it through the publisher's website. And if you're part of our class, you therefore have a license for the textbook, and I've posted that on our Canvas website for you. There's no real self-check questions today. Make sure that you feel comfortable passing values in and out of a function via reference. Remember, when you pass by reference, you can do that as an input, but you can also have it be an output from a function, in addition to any return statement or lack thereof that there might be. Also, make sure that you feel comfortable with the simple algorithms from the last mini lecture. When we talk about searching, we usually are thinking of using a search engine like, Bing, Google, Yahoo, or going way back. My first search engines were Alta Vista and Bigfoot, like 1995. Google was there too, actually, just starting. And so we basically, type some text into a search bar, and then it searches its database or whatever, and then gives you some results and says, here's where you find that thing that you searched for. And it'll be similar for the search algorithms that we consider here for computer science as well, but a little different. We'll use this as our motivating example. Suppose you have two arrays of size n. And later on we'll use n equals 6, but it could be bigger. One of the arrays has a list of area codes in it, like telephone area codes, like 715 for Eau Claire. The other parallel array has the locations corresponding to those elements. So that means that, like, for instance, element number 5 in the area codes, if that was like Eau Claire, then element number 5 in the location array would be like a string that says Eau Claire. So they're going to match up. And our goal is, if somebody typed in an area code, we want to be able to look through that array, the first array, or the area code array, and see if we can find that area code in that array. If we can, then we'll use that location to find its location in the second array. We're going to consider two search algorithms, and today we're going to talk about the linear search algorithm. Next mini lecture, we're going to talk about the binary search algorithm. Let's visualize this. Here are the two arrays going from top to bottom. The left array is the area code array. So area code 0 is 202. Location array element 0 is Washington, D.C. So area code 202 corresponds to Washington, D.C. Area code 1 is 203, and that corresponds to location 1, which is Connecticut, evidently all of Connecticut. And then there may be others, and then at the very, very last one, 802, area code n-1 will correspond to Vermont, which is location array n-2. So again, the first array, the area code array, is an array of integers. The second array is an array of strings. What is the linear search algorithm? Here's what it does in a nutshell. First, we start at the beginning at index equals 0, the very first index of the array that we're searching, and we loop over all of the elements in the area code array. Each time, each iteration, we check whether the current area code at this index matches the one that we're looking for. So if I type in area code 616 for West Michigan, I would go through the first one and say, oh, does 616 match whatever's in the first element of the array? Will it match whatever's in the second element of the array? Will it match in the third one? And if it does, then we want to make note of that index. Where in this array was it? What was that placeholder? What was that index of the array? And if we don't find it, then increment the index at the end of this loop, and then go back and try again at the next index. And keep looping until you find a match. Now that's a keyword, because that might kind of tell us what kind of loop we would want. So I want you to pause this and think about, what kind of loop would this be? We've got for loops, do loops, while loops. Based on this, what is most appropriate? And there may be more than one answer. Otherwise, I'm going to go on and give you some code. Now this is a lot, so let's just take it from the top. What this function does, it's called linear search. It will, if the search is successful, in other words, if it finds the value in the array, then it will return an index to that element in the array. If it's unsuccessful, so for instance, say I type in area code 90210 or something like that. It's not an area code, but say I type that in and the linear search algorithm tries to find area code, I don't know, 90210 in my array of area codes. It's not going to find it there because it's not an area code. And so then at the, if it's unsuccessful, then it will return -1 to denote failure. So that the return value of this function is going to tell us whether it was a success, and if so, it'll be an area code, or sorry, it will be the index of that element in the array, or it will return -1, which means it didn't find that in the array. It just wasn't there. So the algorithm itself, it has int linear search, it'll return an integer, and then const int values. You're going to pass in an array of values like the area codes, wink wink nudge nudge, then an unsigned array size, so how many elements are in the array, and then int value to find. Int value to find is going to be like the area code that somebody types in, and then you're like, hey, is this area code in your database? So that's the key that you're trying to find. That's the search term, if you will. Int position equals 0, that's going to be our first index. Bool found is whether or not we've found it yet. And we're going to do a do loop. So here we're going to loop. We're going to go through it at least once. So if you said while loop, yeah, that's close. There's the until in that last statement. Loop until, that's either a do or a while loop. But we want to go through at least one time, and so that's why it could be a do loop. Again, you could do it other ways. Totally fine. So it's just how I framed it in this one. So we're going to be looping, and we're going to keep looping. We're going to loop at least once, and we're going to keep looping. At the end of each loop, we're going to check, is the position less than the array size? In other words, have we checked all of the elements in this array? And we're going to make sure, we're going to keep looping if we have not found the key yet in that array. So inside, we're going to say if values position equals value to find. So we're going to look at the elements in the values array at the current position, and does that equal the value that we're looking for? If so, then set found equal to true. That'll stop the loop. And if it's not equal to it, then just increment the position counter, and we'll look at the next one in the next iteration of this loop. Okay, so that's the loop. That's done. It'll keep going, and if it finds it, it'll set found equals true, and it will have the value of position. So when we're done with the loop, we either found it or we didn't. So we're going to check the found value to see if we did or not. So if found is true, then return the position. Remember, we want to return the index of this array where we found it. And if we haven't found it, then return -1 to denote failure. Sad. How would we call that? Here's an example main function where you can imagine calling it. So I've set up an array of integers, 6 of them, so 6 area codes and 6 locations. So the int array is 6 different area codes. String locations, the locations array is an array of strings, and this has 6 locations corresponding to the 6 area codes. So that's the thing that we're trying to search. Each one of those is connected. So area code 616, Grand Rapids, Michigan, near where I grew up. Then we're going to ask the user, just for fun, we could just hard code it into the program, but I wanted to ask the user, what area code are you looking for? And then the user says, I'm looking for area code 520. And so then they'll see in that area code 520, and then we're going to do the linear search. So to do that, we call linear search, passing it in the area codes array, passing it the length of that array, 6 elements, and then passing it the requested area code. In other words, the thing that we're looking for. Is area code 520 in that array? And it is, so we know that it should, when this thing, if it's all correct, then it should return element 2, corresponding to the 3rd element in the array. So index should be 2. And then at the end, did the area code array contain the requested area code? If so, or if the index is -1, that means failure, remember, then do an error message and return 1. Or if index is not -1, that means it must have been successful. And then, so print out area code, and then the area code they typed in, like 520, is associated with, and then locations index. Now notice that line with the C out, like the fourth or fifth one from the bottom, notice that doesn't have a semicolon at the end. That's because it's not the, after the is associated with a double quote at the end, that's not actually the end of the line of code. The end of that line of code is actually the next line. It's all one line of code, but I've broken it over two different lines there, because remember, C++ doesn't care about white space. It doesn't care if I've added extra spaces in between things or extra extra tabs or extra new lines. So that's totally valid C++. Anyway, the end result is that I use the array locations with the same index I found for the area code array and print that out. Cool. And I encourage you to go ahead and code this up, see if you can get it to work. Hopefully it does work. It worked for me. But if it doesn't work, let me know, and I'm happy to help. Now for the linear search algorithm, one analogy I like to use is, remember that kid's book where there's like a little baby bird that's going around to all the animals and says, "Are you my mommy? Are you my mommy? Are you my mommy?" Let's imagine that there were 10,000 animals all in a row, and this little bird had to go to each one of them and say, "Are you my mommy? Are you my mommy? Are you my mommy?" To all 1,000 animals maybe. And the actual little bird's mother is one of those. It could be in the beginning, could be in the end. Now, a linear search is basically just that. You start at the beginning of the line and you say, "Are you my mommy? Are you my mommy? Are you what I'm looking for? Are you what I'm looking for? Are you what I'm looking for?" And you keep doing that on and on and on. That would take a long time. But it's really simple. If you have a line of things, you just go through one after the other and you go through it. So advantages, it's really straightforward and easy to implement. It's really easy to say, hey, there's this big old long array of values. I'm trying to find this number. Start at the beginning, work your way until you find it. If you get to the end and you haven't found it, well, then you haven't found it. It also means that the array elements don't have to be in any particular order. They're not sorted by height, by value, or anything. So you can use it on a lot of different arrays. Maybe your values in your array aren't sorted. It has a really big disadvantage that I hinted at before. If that little bird has to go to 1,000 different animals saying, "Are you my mommy?" It would take forever. And indeed, a linear search algorithm is one of the slowest there possibly is. So if you have a really, really big array, 10,000 elements say, this is going to be a really, really long, slow way of doing it. There's much better ways of doing it for a lot of purposes. Computer scientists like to compare different algorithms using something called big O notation. This is an important thing in computer science. They represent that using a capital O and then parentheses, and then in between those parentheses, some function of n. It could be n, it could be 1 over n, it could be n squared, or logarithm of n, but something like that. Now, what is n? N is the problem size for that particular algorithm. For our case, that means how many things are in the array that we have to check. That could be for other things, how many elements are in the matrix, how many pieces of data they have to look at. It could mean a lot of different things for different problems, but generally it's the problem size. Now I want you to think about how many comparisons the previous algorithm, the linear search algorithm, will have to make in order to get the success. So in the best case scenario, how many comparisons will it take? In the worst case scenario, how many iterations will it take? So pause here, think about that, and in a sec I'll go on. Yeah, so the best case scenario is, hey, you get lucky and the thing you were looking for is in the very first spot in that array, so you only go through that loop one time and you're good. Win. The worst case scenario, of course, is if that thing that you're looking for in the array isn't there, or it's the very last thing in the array. So it's like that little bird going around to its, that line of 1,000 animals and saying, "Are you my mommy? Are you my mommy? Are you my mommy?" And it gets to the very last one. It says, "Are you my mommy?" And it's like, "Yes, I am your mommy." And it's like, "Oh shoot, I wish you'd been earlier in the line." Or it's not even there, which is also sad. So in that case, it takes n iterations through the loop. If you have an array size of 1,000, it's going to take 1,000 iterations through that loop till you find what you were looking for. Or you'll find out at the end it wasn't even there. Let's think about the average case now. If the best case scenario is 1 iteration and the worst case scenario is n iterations, then the average case scenario is n plus 1 divided by 2 iterations. So if you have 1,000 things, it's going to take on average about 500 iterations to go through. 500. You're gonna have to make 500 checks, which is a whole lot. Now what we do is we notice that n plus 1 divided by 2 is basically sort of proportional to the processing time that it would take for this algorithm to run. Now, instead we try to reduce that and say instead of n plus 1 divided by 2, we just say it's proportional to n. So the linear search algorithm is therefore of order n. It runs at order n processing speed because the processing speed is proportional to the size of the array. It's proportional to n, the size of the array in our case, or the size of the problem more generally. So if you double the amount of the size of your array, you double the processing time. If you multiply your array, or if you have 10 times more elements, so if you have 10,000 elements instead of 1,000, it's going to take 10 times as long on average. Sometimes you'll get lucky and it'll be really quick. Sometimes it'll be you'll have to go through all of them, but on average, it's going to take a factor of 10 times more if the array is 10 times as long. And again, this is called big O notation. Just one more example here. Remember when you were a kid and you played a game, maybe, at least I did this, maybe you didn't, maybe you were way cooler. But say you played this game where your friend is thinking of a number 1 through 100, and you're like, I'm going to try to guess that number. And then they would tell you, oh, your guess was too high, or your guess was too low. What were the strategies that you used to do that, if any? Well, one would be just pure random guessing. Just guess random numbers and hope that you don't guess the same number twice because then you lose a turn. It's not so great. Another way is to do brute force, to guess the lowest number and go all the way up to the highest. So guess 1, guess 2, guess 3, and it might take a while. Another one is special knowledge. For instance, if you know that your friend's or your CS professor's favorite number is 36, you might think that maybe I should guess that right away, or at least guess that pretty early, and then maybe go to one of the other strategies. Another way is to divide and conquer. There may be other ways of doing this. Now I want you to think about these 4 different strategies. Which one of these is the most like the linear search algorithm? I'll tell you on the next slide. The algorithm that's most on the previous page that's most like a linear search algorithm is the brute force algorithm, because in that case you're checking every single number in a row. Now you could count from 1, guess 1, 2, 3, 4, 5. You could also count down from 100, guess 100, guess 99, guess 98, and so on. But either way, you're going in a line and checking every element or every possibility in a row until you just brute force it and happen to get it. Or your friend says, haha, I was guessing at 999, you lose. You're like, you jerk. Okay, so what the practice problem is for today is I want you to try implementing that guess a number game that I just described. You as the user are going to choose the number and the computer will try to guess. So we're almost going to make like a sort of AI for the computer. And I want you to try to implement it so the computer uses a linear search algorithm to try to guess your number. So the computer will basically guess and say, hey, is the number this? And then you'll say you're higher or lower or you got it. But loop until the computer guesses the right answer. So here's the algorithm in pseudocode. Have the computer make a guess between 1 and 100. Then the user will input one of the following to say whether, to indicate to the computer whether it's higher or lower. So the user would write greater than symbol if their number is higher than the computer's guess, less than symbol if their number is lower than the computer's guess, or an equal symbol if the computer guessed it right. And then that should tell the computer to stop. So once the computer stopped and seen the equal sign, have the computer print how many guesses it took. So again, I want you to do this first as a linear search algorithm. Do this practice problem now, because next time we're going to do the same practice problem, but we're going to implement the binary search algorithm. So that's it for now. If you have any questions, please let me know. And it was great getting to talk to you, and I hope to hear from you soon. Jess out. Bye.